You had this JE rank of 16.
IIT Kanpur had a better reputation than Delhi, but I found that I couldn't get in because apparently the rank wasn't good enough. I ended up discovering the first millisecond pulsar.
You met this famous Indian origin physicist known as Subramanyam Chandrashekar, who was a Nobel Prize winner. You met him pretty early on in your career, and you came away not very impressed.
This is the weakness of the Indian system, that it was elevating theoretical everything to number one. I just felt that it's better to be a first-rate experimentalist than a second-rate theorist. I love bringing down systems. To blame that on distractions and to take no personal ownership, I refuse to grant that to the young person. Passion without preparation, zero. Lots of preparation with no passion is also zero. Never work on a project unless you have an unfair advantage. I always like to think if you're starting something, you should also immediately put in your head the ending date, because it clarifies very clearly what you want to do. I know this will get many people upset. I feel Indian astronomy has now become irrelevant on the international scene.
Shri, welcome to SparX. Looking forward to having this conversation with you. I think over the lunch, something caught my eye. You mentioned that you had this JE rank of 16 and you chose to go into physics. And that too, the physics was such highly contended, across Kanpur and Delhi. Must be quite a different time. So just let's start with that. Your motivation at that time. Today, if you are first of all, if you're in JE top 100, you are a superstar, and it's only computer science, and there is, no physics is nowhere in the picture. So what was the thought process like? What attracted you to physics, despite getting such an amazing rank?
First of all, I didn't even know about the IIT exam because I grew up in Hubli. It used to be a small town now, and now it's a big town. But I went to a good school, Central School, Kendriya Vidyalaya, so teachers were very good. And I knew that I wanted to go into research, but not exactly. Roughly physics, not so much. Biology is definitely not. Chemistry, I felt I had some. So I'd go to the Karnataka University Library and read up Scientific American, trying to understand these things. Because I don't think we were getting Scientific American then anywhere. In fact, the way I even went to IIT is an accident, because in those days, IISc here in Bangalore would have been a place. I think they didn't offer BSc then. So the thing is, you do BSc and then you come here for MSc.
Correct.
But someone told me that IITs have started and they're doing a integrated physics course. So I didn't know what the IIT was. So actually, then I went and talked to someone else in other part of Hubli, and now I can tell you who that is. That's Ravi Deshpande.
Okay.
Went to IIT Madras. And he said, it's not, you have to apply and appear for an exam. And I said, what is this exam? And he said he didn't know enough about, he's about, I think, 5 or 6 years older than me. Then he said, but this is other guy who's just took the exam last year. You should go talk to him. And so I went to the Harvard and I met Nandan Nilekane. And he told me there's a book called IIT exam book. Which I ordered. It was last 5 years of exams. And I sat and, systematically solved across the 5 years. And then a month later went and appeared for the exam. And so it wasn't some big preparation like what I was thinking. And
I'm almost thinking we should edit out this part. We'll give a lot of people a lot of complex, because now there is a 4-year rigorous process, and you just effectively you're saying you walk in and you end up with this incredible rank.
And then I didn't know much, but IIT Kanpur had a better reputation than Delhi. And but I found that I couldn't get in because apparently the rank wasn't good enough. So I got into IIT Delhi. They're the only two IITs doing what was then called integrated physics, and now I think it's called engineering physics.
Yeah, and somewhere along the way, you developed your interest in astrophysics. You knew beforehand, or it was?
Roughly because of reading Scientific American, it looked very interesting, but there's no astronomy in school, and certainly not in, IIT. That
I should say astronomy or astrophysics.
That's part straightforward. Astronomy is sort of collection of the facts and the data and so on. Astrophysics is when you interpret this. Either is fine.
All right.
Okay, it makes no difference. In some sense, astronomy is preferred. Uh, but I had a science talent scholarship, and apart from the scholarship, they allowed you could go to a summer school every summer. So
Yeah.
first year I went to BITS Pilani, and what the theme was chosen by that host institute. I think it was more on nuclear physics. You looked at some emulsified water detectors and tracks and measured things, that sort of stuff. I'm not sure exactly, I don't remember well. But after that one hot summer in Pilani, I said the future summer schools will be decided not by topic but by location. Okay, you don't want to be in summer in Pilani, I can tell you that.
Yeah.
Anyway, but 2 years later, there was a summer school right here in this institute at RRI. It was the first ever summer school in astrophysics. Radhakrishnan, who had come back, was the director, and he brought with him a few young people. This institute was very young at that point, effectively.
Yeah.
And that started a major program in radio astronomy. And then, because it's a summer school, Govind Swarup, all the TI for radio group was here. Then the Indian Institute of Astrophysics and Corman, they were also here. So that summer school, I realized this is what I want to do, and in particular, radio astronomy.
Right. And then you went for your, I think, PhD in US, and from what I understand, you hit upon something pretty significant during your PhD years.
Yeah, so I went to do experimental radio astronomy again. There's a faculty here, Rajaram Nityanand. I wanted to do my work with him, but he thought if I want to do experimental work, probably the US would be better. So I only applied again, like my JE exam. I said, okay, I'm quite happy being here. And then he said, you should either go to Caltech or Berkeley. So I applied to those two places. That's it. And Avi was there, I figured it's fine, if not. And then Caltech rejected me, and then Berkeley took me. So the decision was easy.
Well, you got the revenge, and then you were
Yes,
faculty
I got
there
the
for...
revenge back after coming there. Right. Yeah, so Berkeley was a very exciting place. There were several professors for radio astronomy, low frequency, mid frequency, high frequency, and very experimental nature. And Charles Towns, the inventor of laser, had decided to work in infrared astronomy. So it was a buzzing place. Anyway, towards the end of my thesis, it's a long story. I've written up an account of that recently. I ended up discovering the first millisecond pulsar, which was not expected at all at that point. And so it was a pretty sensational discovery in itself. But add to that was found, by a grad student.
It's incredible. Just maybe for our listeners, can you just help describe what is a millisecond pulsar? What's the significance?
Yes. So if you consider a star which is, let's say, 10 times or more than that of the sun, then they'll end their life as a neutron star. When I say end their life, is that all these stars are fusion reactors. The sun is in its center, as we speak, fusing hydrogen to helium. So at some point, you fused in the interior part, most of the hydrogen in the interior is now helium.
Yeah.
Now, if it is massive enough, you can get to the next fusion reaction, which is helium to carbon. That lasts for a short time. Then you'll only have carbon. Okay, then you can start burning carbon. But very quickly, as these fusion reactors go up and up in the periodic table, as it were, you reach a point where you're now about to produce iron. But iron is a very stable, it's the most compact nucleus. So iron forms a dividing mark. Elements below iron, you can fuse and gain energy. But elements above, meaning with higher nuclear charge, you can do fission. So iron is stable. Think of it as a valley. You can gain energy either on either side of the valley, but not in the valley.
Right.
And so that stops, and the star collapses and becomes a ball of neutrons. Largely neutrons with some small percentage of electrons and protons. And the size of the mass of this neutron star is maybe 1.5 times that of our own sun. But the size will be much smaller than Bangalore, only 10 kilometers across.
Wow. Extremely dense.
Yeah, it's the most dense matter. We don't know anything more dense than that, because if you compress a neutron star, theoretically speaking, it'll become a black hole, and then you don't talk of things like density anymore.
Right.
So the first evidence of a neutron star was in the form of a pulsar. That is, some of these neutron stars are magnetized and they're rotating. And that leads to like a lighthouse. Think of a lighthouse and this ball.
Yeah.
It has two painted spots. And think of this, instead of the spots being on the axis of rotation offset, then every time you see one of the spots, you're getting a flash of light. So that's why it's called pulsating radio source. Pulsar. Okay.
And we can only watch the ones which are pointing at us.
Yes. And that's called the beaming fraction, and maybe it's as small as 1/10. That is, for every one you see, the 9 you're not seeing. Okay. And the general lower, the first ones were found was the second, and the general lower were they're born at about a tenth of a second, or maybe a little less than that. So, which made sense, because the fastest pulsar, the youngest pulsar, was the Crab pulsar, which is only 30 milliseconds today. And we believe when it was born, it was only 15 or 6 milliseconds. So the idea that you can get a millisecond pulsar, meaning this 10-kilometer radius object is rotating 642 times a minute. So it is faster than your kitchen blender. Your kitchen blender is a small thing, so you can imagine, but this is a big thing.
Yeah.
So that is not so obvious how nature makes that.
So that was the very first millisecond pulsar. Yes. Was it theoretically predicted at least, or it was just bang from the blue? Just
that's why the field, everyone in pulsars thought the field is first pulsar discovered 67, 68, and binary pulsar in 75, and then more or less it seemed like in steady state, and suddenly this came and gave a huge burst. And even today, even though discovery is so long, even today, the big search is going on for millisecond pulsars. And the main reason, there are several reasons. The first one is that what do you have? They're incredible clocks. Okay. They're very stable clocks. So they have a stability of maybe 1 part in 10 to the 14, 10 to the 15, which is very, very long.
Yeah.
I mean, that's an exquisite clock. But most importantly, they're not bound to us. So we have better clocks on Earth, but they're subject to the gravitational field of the Earth, the rotation around, they are not inertial clocks. These are far away, they're inertial clocks. So you can imagine actually using a whole bunch of these millisecond pulsars and imagine Earth here and then all these things. So what you can see then is you can actually measure the distance effectively. If you time them or in a year's time or add up the data, you could be getting to, speed of light is roughly a foot per nanosecond. So we have 30 nanoseconds, it's 30 feet. That's amazing, because you're now measuring the distance. So this immediately makes this into a gravitational wave interferometer, which is sensitive to periods of gravitational waves, period of, a year or longer. So-called long wavelength gravitational waves. And that's a major thing. So last year, astronomers, after pursuing a dozen of these for a long time, found evidence of some long wavelength gravitational waves. Okay, so this can come from binary black holes, which are very massive, or even from the early universe. So it's a big part of the LIGO story, if you wish, or gravitational. LIGO does wavelengths or frequencies which are, let's say, 10 hertz to 100 hertz, whereas these do wavelengths which are like, a year, which means the frequency is something like a tenth of a microhertz. Okay, so on the other end.
Yeah. Got it. So you had this, this big finding around millisecond pulsar. Yeah. I'm sure, and as you say, it was very well noticed. So you must have, this was in your 20s, and you must have obviously felt pretty good. But how did that, also change your outlook about what you wanted to study in the, coming years and decades?
Yeah, it was in some sense. How do yeah, of course, all such things that I would certainly a lot of it is luck, maybe most of it. But as a graduate student, I had already decided that um, for my thesis, I didn't want to work on any topic at all. The usual approach is you choose a problem, which is supposedly interesting, and hopefully interesting, and then you work away, and 3 years is the usual hardcore time for doing thesis, and then you hope to make some breakthrough or some solutions or whatever. And so I had already taken a decision, I don't know when, maybe even at IIT, that I thought there are other ways to doing science, which is, and maybe after the summer school, because which is I thought I will learn all the techniques in a particular field and become a master of all those techniques, and then apply as and needed for that problem. So sort of a little bit of an inverted thing.
Yeah.
So in that sense, the pulsar thing was not an accident, because even though my thesis was in the study of diffuse matter between galaxies and instrumentation, I'd already learned almost all the observational techniques and good amount of instrumentation, radio astronomy. So I was able to work on something completely different, even though as a thesis student.
Got it. And I think, I'm recalling one story, Shri, you told me, the first time I met you, about you met this famous Indian origin physicist, as Subramanyam Chandrashekar, who was a Nobel Prize winner, and you met him pretty early on in your career, and you came away not very impressed.
Well, let me, obviously, Chandrasekhar is, was an absolutely eminent astrophysicist. I have no issues at all. Not no issues. I mean, something it's undeniable, I would say. But I had to say I'd already had formed some bias in general against that style. And I thought, this I thought through very clearly in the long journeys I took from Hubli to Delhi twice a year, about 50 hours of train journey, that I thought after I knew I wanted to do astronomy or in general research, that at that time in the 70s, a lot of, when you say research or you say physics, it really meant theoretical physics. And that was considered as the highest end. Now, if you're doing something like semiconductors, then you have this guy who's just a technician who's trying to modify this and that. There's a definite hierarchy of what is considered interest or high value. And I knew right away that I thought, in fact, this is the weakness of the Indian system, that it was elevating theoretical everything to number one.
Yeah.
And my view on that is it's wrong for two reasons. One is the science is not just theoretical part. It is about reality. It requires measurements. It requires hypothesizing, which is creativity. And it requires mathematical ability to convert those statements into mathematical statements. The solutions then allow, it's a very wholesome activity. So to have a singular focus on one aspect of that makes you, in fact, limited.
Yeah.
One person can do that, but if a whole country has a thing like that, then that the country is limited, right? Or that society. That's number one. The second one is we have very different talents. It's, and this I really, really felt very strongly, that by setting up a fashion or expectation of theoretical physics is like great. You're telling everyone, all these young people, even though if they may not be good at, theoretical physics requires a bit more mathematical mind, and maybe it's not for everyone. And it's not a law saying, oh yeah, I don't have a mathematical mind, so what, I mean, the point of life is you maximize on what you have. There's no point denying reality. So I just felt that it's better to be a first-rate experimentalist than a second-rate theorist. Anyway, so you can see that one of the objections I had learning stellar structure in my first year at grad school in Berkeley was there's a classical book on stellar structure and stellar structure by Chandrashekar. It's but he had statements like a theorem and a lemma. This is a book on stars. Stars are not mathematical objects. They actually are things. And it's okay to convert a star into a simple approximation for convenience. Okay, let it be round. It's a very good approximation. But you can't then say, it has only a radial dependence and so on. Yeah, you can. But the real star actually has convection. That will never be captured into this. It has a radiation and convection back to convection or radiation and so on. And you can't capture that. That is actually a numerical analysis problem. So you can't make I felt even as a student then that is actually very silly to have a book on astronomy and treat it as an exercise in mathematics. So I had already, if you wish, a little bit of a prejudice against this. So in 85, I had gone to Chicago to give a talk. This was a millisecond pulsar, which I discovered in 82, and I just started at 85 at Caltech. And so I said, I'd like to meet, of course, the great man Chandrashekar. And so he said, what are you doing? And, and I told him I was very excited. I said, I found the first millisecond pulsar. I'm looking for other such I said, the big hope is, first I mentioned this gravitational wave sort of thing. But I said, it's too early. I mean, but I said, it's possible 30, 40 years from now, this will be reached. And it has taken literally that much short of time. But I said, the second one, it'll be great to find a millisecond pulsar around a black hole. Okay. Then you'll get all the GR effects, like light bending, eclipsing, Shapiro delay, precessional Perry-Aston, spin-orbit coupling. I mean, these will be amazing GR effects to And then he said something which only reaffirmed my prejudice, let me put it this way. He said, GR is such a beautiful theory, it needs no verification. And then I said, internally I said, you are a great scientist, but this is actually not a great statement.
Fair. No, I think the reason I brought up that story also, and a little bit on getting to know you, Shri, I've also realized, you had a healthy, disrespect of authority and a little bit of this rebellious streak, doing your thing, speaking your mind freely, which I think, for a scientist, is probably a good trait because, you're always in some ways, every progress in science in some ways invalidating, what has been done before or changing thought process, right? So that's just been who you've been throughout, or you had to cultivate and nurture it?
I've always been, I love bringing down systems. Maybe later when we talk with the Zwicky Transient facility, I can come back to that particular theme. My view is I don't actually see it as an antagonistic thing, even though many people seem to. I have a very simple view of science. Science is exploring reality, and how you feel about it and how I feel about it, it's completely irrelevant. And B, irrelevant in the sense it'll make no difference to the universe. The universe is not really particularly worried about, let's say you have a model, it's working well, and then I have another counter model, it's something else, and then we get a new observation, and your model looks better than mine, and so on. Okay, fine. But in the end, it's just a model. It's not reality. It's just a construct that we have made. And those constructs don't have lasting value. But if you start thinking it as a lasting value, then in my mind, you're a religious guy, okay? And then it's over. There's no discussion.
Yeah. Something, you said earlier also caught, my attention. And I think it's probably very relevant for youngsters today. You mentioned two things, there's 50-hour-long train rides from Hubli to Delhi and a lot of thinking on those train rides. Yes. I realize, today's youngsters are deprived of that, thinking time. We have all our phones, social media, short attention span, 2.5-hour flight from Bangalore to Delhi and so on. What do you think? Is that a bit of a loss? And even growing up, I remember a lot of time being bored, nothing to do, just pacing around the house and thinking, about big grand things in life or whatever it is, but engaging with your mind. Versus today, it's not easy.
I'm sorry, I have a little respect for someone who is a young person, says, I have my iPhone, this. It's a choice you're making, and choices have consequences. So if you're smart, you have to understand there are many ways you can spend life, right? Even in the old days, what's to prevent you from going on the train and reading a novel? There's nothing wrong. Or you could have read okay, maybe there's more distractions today. But to blame that on distractions and to take no personal ownership, I refuse to grant that to the young person.
But the important, irrespective of that, let's say you take personal ownership, but there's something to that, and finding the
Yes.
free time and engaging,
No,
with
I
the
think it's a thing you have to cultivate. So I remember recently, I gave a seminar just earlier this week at IIT Mumbai, and this is a standard
yeah,
question I do with actually all sorts of young people, and these are the creme de la creme of the country. They've gone through this
Yeah.
JEE exam, and many of these guys are apparently with a lot of preparation these days.
right.
All that sort of stuff. Okay, fine. So I was giving a seminar, and I said, no, this wasn't a question answer thing, just some students. I said, how many guys have flown on an airplane? And everyone said, yeah, they have. I said, okay, tell me what is the speed of the airplane? Okay.
1,000 kilometer per hour.
Yeah, but many couldn't. And then I said, did you see, one of the channels in an airplane, in most airlines, it tells you the height, the tailwind or headwind, the temperature outside, okay? So I asked them, do you know what is the rate of the fall of temperature with height? Okay, so which is dt or dh. D is the temperature, h is the height. That's an important thing to know. And most importantly, can you compute that from first principle?
Yeah.
And also, once you know the speed of the airplane, what do you think is its relation to the speed of sound? Which meant you have to compute the speed of sound or know it.
Yeah.
Better still, both. And no one had done that. I said, yeah, that's because all of you make a choice. When you get in a plane, you want to watch a movie or some stupid cricket game or whatever, right? You made a choice, and choices have consequences. So I absolutely refuse to give any sympathy for people. If you're a scientist, you have to be absolutely devoted and immersed in it. And if you're not, look, you don't need many scientists in the country, okay? Maybe 1 in 10,000 of the graduates, maybe even less. But the people you do need, they need two things. They need to have absolute passion for this and knowledge to go with it. One without the other is useless.
Right.
Passion without preparation, zero. Lots of preparation with no passion is also zero.
Okay. Right. No, got it. Let me go back to your research career, Shri. So, what are some of the big questions that occupied most of your professional life? And I know you made seminal contribution to the field. You've been very widely acknowledged. Recently Shaw Award, which is extremely prestigious honor in physics. But just talk about some of the 2-3 big questions that occupied most of your professional career as a scientist.
Yeah, so part of it is as I told you early on, I decided that I don't want to, in some sense, ask a question and then answer it, which is a classical approach.
Yeah.
And it's perfectly fine. I'm not denying the value of that at all.
Yeah.
Okay, there is some value in actually saying, I propose a hypothesis for whatever reason, and I'll take measurements and see if the observations agree with the hypothesis. It's a very classical approach, as opposed to just, doing some aimless wandering. Nonetheless, so my approach has been identify potential, basically identify technology which will potentially change the game in astrophysics. This is technological changes that relate to astrophysics, okay? And then use them after having read a bit about that subject to make some advances. So I would say the closest to your word is I guess I've done about 5 serial entrepreneur, about 5 of them in my life. And the approach is the same as any entrepreneur, right? First you have to come up with an idea that is obviously not so common. And then you have to sell that idea to someone. In your case, it'll be to VC or someone else. In my case, it's to funding agencies or to other young people. Say, come and let's go and do something. And then at some point, you need a huge capital to actually get the program in production mode. So that's been the approach I've used. And about every 5 or 8 years, and then once I'm done, and it's a highly successful endeavor, after about a few years, I just leave the field. Because now it becomes, you're competing
Yeah.
in a more broad arena. So the three things I would say, if you ask me, um, uh, the millisecond pulsar was not, in some sense, not exactly a part of that sort of stuff. But the first big one was brown dwarfs, I would say, where I thought the technology, electromechanical technology was getting cheaper. So
Yeah.
when you make an image of a star through a telescope, when you see stars on a especially hot summer evening, you'll see they're shimmering, okay? That means the atmosphere is actually unsteady.
Yeah.
So the rays come in and they get bent and so on. But if you could have a mirror that's flexible and you do the opposite, then you can sharpen the image.
Yeah.
It's called adaptive optics. And that was coming up in the 90s, early 90s. So I thought, why not get into this and make very high contrast, high dynamic range images
Yeah.
and look at nearby stars and just go to see, how faint can we go? That is the engineering
Right.
technical approach.
Because these brown dwarfs are by definition very hard to see.
Exactly. And then there's always, but hope is not a plan. So the thing was, whenever you plan these sorts of things, in my mind, you should always have a thing which says, I'll find some things, I can write a paper. And now it may not be a winning paper in the sense like something fantastic, but it should be a valuable paper. So I thought, okay, faint companions to nearby bright stars. We'll do a complete catalog. This is classical astronomy, actually. And that led to brown dwarf because we had the ability to actually really go deep and find this very faint companion. And we found that it was attached to it because a year later, the distance between the two was still the same and all that sort of stuff. So that's a field. And so I worked in that field roughly from, 93 to 97 and then left after writing about a dozen papers.
And these brown dwarfs are just, are these failed stars? Just two
Yeah, there
small...
are sometimes they're called either failed stars or highly successful planets, which depending on whether glass is half full or half empty.
Fair, yeah.
So Jupiter is at the low end of a brown dwarf, if you wish.
Okay.
It's a ball of hydrogen, helium, and no fusion. And then if you keep scaling up Jupiter, just add more and more hydrogen and helium, up until it reaches about 80 times its own mass. There's no fusion, but about 80 fusion reaction sets in. So brown dwarfs are in between stars, which stops at 80 Jupiter masses, and sort of massive planets like Jupiter, which may be a few Jupiter masses. So that's the regime.
And then you were observing them indirectly because they don't have much
We found them. This is direct imaging.
direct imaging. So because there is a faint glow coming out of them.
Yes, and then we were able to get spectra and all that.
Got
That's
it.
Yeah.
Got it. Okay, so this brown dwarf was the first big project.
Another one was less to do with technology, I would say, but more to do with understanding that I decided to switch into X-ray astronomy, went to Japan for a few months, sabbatical. I learned a new field called gamma ray bursts. And after I came back, I realized there's a new European mission that was going to go up. And I thought this might help solve a mystery at that point.
Yeah, and before we proceed, maybe we'll ask you again a tiny bit of science lesson. What is gamma ray burst and where does it come from?
So in the late 60s, it was observed by US military spacecraft that, randomly somewhere in the sky, there's a bright flash in gamma rays. And it was random. And over the next 30 years, there's a large number of investigation. And now I can tell you it's about maybe 1,000 a year. And it's isotropic. The chance of seeing a gamma ray burst here is the same as seeing there or anywhere else. Okay. And there's a big debate. Where are they? Are they in our own galaxy? Are they in other galaxies? Are they across the universe?
And when we detect them, they last for a long time or they...
Ranging from few seconds to maybe a minute.
Got it.
Okay, a few minutes at most.
Extremely energetic.
Yes. And so my colleague and I got into this in 96, just about the time of the launch of this Italian-Dutch mission called BeppoSAX. And to make the story short, we were able to detect that even after the gamma ray bursts that faded away, that later you could see radio emission. Another group had found optical emission and X-ray emission, that's called radio afterglow. And then we were able to use the Keck telescope and study this late optical emission and show that this gamma ray burst came not from the just nearby galaxy, but across the universe. So when you multiply what you observe to get the luminosity, they're like absolutely the brightest explosions in the universe.
And what is the source?
We now believe these are the birth cries of newly born black holes.
Ah, okay. And maybe to understand this, the black hole formation must be a process. I presume it's a very involved process.
Yeah.
Why do we see this burst versus a short period of time?
Yeah, I can't give a simple, immediate answer on that.
Is this what we now know for a fact, or is this that this is the only source for these,
No, what we know for a fact is that if you look at the same place with the gamma ray burst, after it has disappeared, you will see an exploded star. Okay. And then we have theories of what this is.
Got it. And that's the optical signature that you...
Yeah, no, the exploded star comes many days later. The optical comes in between. It's called the afterglow. But anyway.
Got it. Understood. Okay, so this was, the kind of next big project.
This was a very fruitful many years.
Yeah.
And so the last one I would talk is the Zwicky Transit Facility. So gamma ray burst was extremely fruitful. So about 2004, when I was returning from Cape Canaveral, because NASA had decided to launch a big mission to study gamma ray systematically. And with this mission called SWIFT, they're going to study, they're hoping to localize 100 gamma ray bursts a year. So we went from one every month to 100. So I thought this is the time to leave, because now it's the mass market. Okay, then I have no special thing.
And this Zwicky Transit Facility the idea was to in some ways automate, astronomy used to be, this slow, laborious process. You crawl under a telescope, watch all night, and maybe observe something. But this is like different industrial scale of doing things.
When I was coming back, I was thinking what to do next. Then usually when I do this, it takes me about 2 years of thinking and understanding, what the opportunities are. And also one maxim I have is a simple one, which sounds a bit strange, but this is something I always tell my students and certainly tell myself. My maxim is simple: never work on a project unless you have an unfair advantage. Okay, because there are two ways you can think of science. One is, you're a noble person. You will advance science by being very systematic, and you'll contribute to the general study. Yeah, I would say fine. Mukesh, you're one of these noble people. I don't know you, but not me. For me, it is extremely important that I make the discovery, and I'm in here for that particular reason. Okay, it's a very personal activity. Okay, and I don't understand how anyone can be. I mean, if you're passionate about something and that's all you think about, that by definition you have to be passionate. That means you really have made it a very personal agenda.
Right.
Okay, it's not an agenda on part of humanity.
Yeah, it's also it's a good mental model. It's a filtering process, because there are many possible paths too, but there's probably shortest path. And when thinking where I have unfair advantage, that's where because a lot of people are trying to do the same thing. It applies to startups also. This other day I was talking to a startup I'm involved in. I was just saying, what is the shortest 3-step to define your endpoint, and among all possible paths, least action, what are the shortest step path you can devise to get there?
Yeah. So I then realized I was teaching, one of the. This I think is a very important point I'm making. Place like Caltech is what's called in the US an R1 university, which is, you can have a university, or probably the correct word is a college. A college is what you'd think. It's a 4-year, 3-year college where you teach. Primarily the professors teach a lot.
Yeah.
That is sort of the expectation. I would say the amazing success, post-World War II of the U.S. universities, I would say it's absolutely related to the fact that U.S. has the largest number of very high-quality R1 universities. There are two ways to do research. Okay, one is you have research institutes. Okay, you bring in people who are focused on research, star hires and so on. For example, in Germany, they have the Max Planck system. It's even not just a research institute, it's a research institute built for a particular person. They actually hire someone in their late 30s who's very promising and give huge amount of resources to this person. Okay, and that's one model. Okay, and locally, RRI, TIFR, ISC, though that has changed a bit recently. That's another okay. One of the reason I think the R1 university model is a success is a very simple thing, and it's noted in Feynman's autobiography, where he says somewhere, when you want to research, teach. When you want to teach, research. So all my new ideas or big changes in what I've seen have come about from teaching. So as I decided to teach a new class. And one of the problems I was working on that is if you have two neutron stars and they merge, which happens, that's in fact the start of the LIGO story. And so a lot of discussions are going on at LIGO. And it's been thought through. But I thought, okay, a very simple idea is if they merge and the neutrons are now set free, then they start decaying in about 10 minutes. So the question I asked is, if I have a small fraction of these neutrons are decaying, they'll produce a glow. Is this detectable? And I was surprised due to variety of physical effects that even though the decay happens in 10 minutes, that actually you can see this glow on time scales of a day. Okay, because the photons take a while to diffuse. That's what it is. Then I said, well, that's interesting. But they're rare. Okay. So I thought, okay, we need to build a machine that has got very large field of view to find this literally needle in a haystack. But all the approaches then were more manual. Okay. And they're all targeting supernovae, which take days to rise, weeks to decay. So everything could be done. And so the best search that was happening was sort of a manual one, and they're finding about 100 supernovae in a year by targeting nearby galaxies. And because I have you may have sensed, I have a huge, I always look at all these problems first as an engineering problem. Okay. I said, why do we need to do any of this manually? Why can't we automate the whole thing? So roughly, over time, I got the idea to basically build, to industrialize this process. Okay, so no humans in the loop. So if you look at the highest industrial efficiency, the first one is in manufacturing, you have line, and in a line you specialize different things to different. Okay, and then the conveyor belts moves from A to B and C. Okay, then if you want to do pattern recognition, you can use algorithms. So that led to something called the Palomar Transit Factory, and in fact, a very interesting person kick-started this process. I was explaining this idea to a friend in Santa Barbara, and he introduced me to this old gentleman who took me out for lunch. I explained this idea, and turned out he had a storied career and had retired to Santa Barbara. He was the vice president for research in Data General, and after that in Sunworks Systems, and after that in Google, and they had retired and obviously is well off. So he really liked the idea, and he gave me the money to start this project called Palomar Transit Factory. And another rule I have is I always like to think if you're starting something, you should also immediately put in your head the ending date, because it clarifies very clearly what you want to do. And I think this is a mistake most people, this I would say you have to be a little analytical about it, because most people start some projects, and sometimes the correct answer is, if you're starting a company, right, like IBM, or small or whatever, or Microsoft or Infosys or whatever, you're not starting it for 3 years. So I'm not applying, but that's not the world I operate. My thing is, as you understood, I want to be there, make all the early things, and then leave, which means you should have an exit plan clearly understood in your head. Because if you don't have that, then you start wasting time. You're not optimally using your resources. There's a huge difference when you start a project, say, I have only 1,000 nights to finish this, which is 3 years by the way. Then not saying anything. The moment you say that I have 1,000 nights, then you say, wow, one night's finished, second night's finished.
Yeah.
There's an urgency that that brings to you. Anyway, so I thought PTF, because there's another competing project in Hawaii funded by the Air Force. They were getting $10 million a year. The money I got from Mr. Rosing and matched by the rest of the world was over $3 million altogether over 4 years. So there's no competition. I thought, at some point these guys will beat me. But then I realized that they were trying to do everything. And then I said, we'll focus on transients. That's why the name is Palomar Transient Factory. It's exactly correct. It's at Palomar. It focuses only on transients and it's a factory.
Got it.
Okay, and they were trying to do a whole facility.
Right.
Anyway, it's such a success that at this point, I was myself surprised. I thought about 3 years later I'll be shutting it down. But the US had started a program called LSST, which was basically like the Palomar Transient Factory, but much bigger.
Yeah.
$1 billion project. And this is where a bit of my anti-establishment came. I said, why don't we do like a pilot project now? Because these guys will take 10 years. And we finish and then we'll do all the easy stuff. Yeah. So that led to the Zwicky Transient facility where that became a much larger project. We went from 3 million to 30 million at this point, a large number of things. Yeah, so that really relied on two ideas. One is this idea that you can see this rare phenomena if you have the grasp.
Yeah.
Other one is I'd been keeping track of the price of silicon sensors, namely CCDs, per dollars per pixel for a long time. And I thought by somewhere about 2013 or 14, it would be affordable because it was following essentially a Moore's law. And so from PTF to ZTF, we did this big jump, but the detector costs were affordable. Had we done that 5 years before, it would have been not affordable to us. Right. Okay, that's sort of the timing that I think correctly.
Yeah, just like any startup, getting timing right. I think this is a great framework for having end goal in mind, so that you have the sense of urgency as opposed to leisurely, you just see as a rolling by and so on. So I guess this whole Zwicky Transient facility, etc., is a probably, I'm guessing, is a transition of astronomy from this, you have these astronomers spending all night, with some telescope. I'm sure you must have done tons and tons of those. To the sky is vast, and we so much more to observe. So this is probably the future where we can really on an industrial scale automate and observe all kind of signals, automatically process, and probably dramatically accelerate. What we are able to understand.
ZTF is already doing that. There's no one up at night. It's run with no humans in the loop. Yeah. Not only does it run the pipelines in real time, identify interesting objects, usually contextual information, rank order importance like a human would, and then pass the topmost candidates for further follow-up, and then report the outcome. Yeah. So when I come in the morning, there are things that are already done.
And having observed everything you observed, and over last 30, 40 years, you feel good about how much we know, or you still feel how little we know?
I'm always happy with how much we know, because that, is it Einstein who said, what did he say? I forget what it is. Maybe it's something like, imagine a sphere, which is the knowledge sphere. It keeps expanding, which is good. So you can look in and see the volume is increasing, quite big actually, R cube. But then ignorance is R squared. R is also increasing.
Right. Right.
No, I think we should rejoice at how. I don't see any reason not to rejoice.
Right. And optimistic about what all we may find in next few decades?
Yeah, I think so. As long as we can keep our world in order.
That's the problem.
That I don't guess, but I think the pace of innovation and pace of discovery is not slowing down at all. In fact, it's amazingly moving fast.
What are some of the, if you have to just wish, and I guess maybe it's your not style to wish, few answers you would like anyone in the world to find out in next, this 20-year horizon, there's something.
Yeah, you guess, right? I don't have this sort of idea of wishing, because that's sort of like you seeking, you have a thing you want to go and answer. And and I know there's a standard wish list. What is dark matter? What is dark energy? Okay, and then if you're really very speculative, what happened before the Big Bang? I don't know. And I'm a bit, my view is that I don't want to to wish. I just want to see what are the opportunities and do that.
So we do just good science, we find what we find.
Yeah.
Yeah, fair. Okay, that's one way, and I guess maybe keeps you a lot more curious versus, project driven. In this case, your eyes wide open. Shri, you've been spending, you're quite actively engaged with, various research institutes in India. So maybe let's first start there. What's the motivation? What kind of engagement you are able to find with, research interest institutes that are of interest to you?
Yeah. So, first I was born here and educated by the taxpayers of India, for which laid my foundation. I definitely owe a debt of gratitude. And I'd like to see a country of 1.4 billion, stand, has its own rightful place in this world. I'm also in general interested in similar things for Asia. So I have actually a lot of engagement with East Asian countries, Japan and China. And recently I've been also got engaged, more engagement with Taiwan. Recently, we had a meeting in Taiwan that was organized on some ideas of how to pursue this style of astronomy, which are called as looking sideways in Taiwan. And at the end of that meeting, I posed a question to all the audience. They're all from certainly many countries in Asia, even Chile, certainly the US also, China, Japan, Korea, Taiwan, India, Malaysia, Thailand, I think, yeah. I asked the following question: why does Asian astronomy continue to lag behind Western astronomy? And here there's a difference. Of these countries I mentioned, India is the poorest. Our per capita GDP is maybe $2,500. And surprisingly, within maybe $5,000, Korea, South Korea, Japan, and Taiwan are similar now, between 30 and 40,000 per person.
Yeah.
China is maybe 15, 17,000. I don't know. I've not kept up. Okay, so there's a range here.
Yeah.
And so in the past, the idea was that a lot of science is capital intensive, and therefore it is clear Asia isn't doing well. But of course, that is increasingly less true, certainly for East Asia. Okay? And even India is economically growing, but of course not as fast as they have grown. So it's perhaps not as strong a statement one can make. Also, I don't know what fraction of GDP we are actually devoting to research. I'm told
about 0.4%.
Yeah, I'm told that's below sort of what OECD countries do. Okay, so yes, there is an underinvestment, or there could be more, let me put it this way. So for many years, anyway, that's a background. So for many years, I've been trying to, I give talks, and I spent like a few years ago at TIFR in Colaba under one of their programs, and I taught a class here, taught a class at IA, many courses. I've been doing that sort of stuff, and working with Indian colleagues. I was a part of the group that helped India join the TMT project. I helped other colleagues who wanted to join LIGO, which this institute has a fairly big role also. So in some ways, and in the same way, these other countries like Japan, Korea, Taiwan, they're also investing in mega projects. Of course, Japan earlier because it's been rich for longer than these other countries. But now Taiwan, Korea are investing money like we have in mega projects too. But I've now come to the conclusion that we are not, that we really should ask this question very clearly. And it's not meant to be criticized in the sense that it's not so much to find fault or to get a blame, but to simply face reality. And I know this sounds very harsh, but let me say it because I realized this time, I was in Taiwan for 2 weeks. After the meeting, I was coming back thinking about this all the time. I realized that in the 60s and 70s, the differential between India and these East Asian countries was modest.
Yeah.
In fact, there's no astronomy in Taiwan and Korea that I can even relate to. China, almost nothing, because Mao's great leap, what I call as great leap backward, country back. And Japanese had programs with TIFR for balloon flights, X-ray astronomy. We had some amazing theorists. Radio astronomy were some of the pioneers.
Yeah.
But let's fast forward to the year 2025. All these other countries have made progress. Our progress we have made some, but it's the differential has increased. And I feel at this point, even though it sounds an alarmist statement, I feel Indian astronomy has now become irrelevant on the international scene. I know this will get many people upset, but I'm saying please listen to the facts. I'm telling you, what is it that the external world will miss? Yes, I would say GMRT is one of the crown jewels of the country. It's a very simple way to evaluate. Do outside people want to come and visit you? The answer is yes for GMRT. Do they really want us to visit for other things? Okay. No, and the reason I did this is we did a big polling of all the young people collected in Taiwan for this meeting. And I asked them questions. Where would you like to go as a grad student, as a postdoc, as a faculty member, as a sabbatical visitor? And as they gave their answers with this QR code and all that, a dot came on the world map which was projected. And they're largely in US, a bit in Western Europe, maybe a dot or two in Japan and Australia. This is a fact I'm quoting to you. And then I would say we should face this fact and say we have a problem. And this problem, for a long time, I thought was primarily first and foremost money. Second, I thought it's governance in the way the government restrictions and all the way this happens. But I've now come to realize there's some completely separate problem, which is the way these institutes are organized. I think they're wrong, actually. So I know it's this. I would say many people will be surprised. I would say that if you look at a place like, let's look at Caltech. I've been there for 40 plus years, so I know it extremely well, and I've been a somewhat influential member there. And our rule has been very simple. Whatever we do in astronomy or in anything, our goal, our intent is to be the best in that. So let's say we have 15 faculty in astronomy. That's about, we could have two choices. One is we could have comets to cosmology. One faculty member working at the smallest end, nearest things, comets, bunch at the other end, cosmology. We don't do that. But we are a large enough department, we still want to be known for a few things. Now, it doesn't mean that, I'm a star high in cosmology and I'll hire a few underlings. No, all these 15 faculty are independent in their own right, but we work together for a common cause when it makes sense. So a few years ago, I've been got interested in a space mission, and I tried a few times, failed. But then as the failures taught us, and then I involved more colleagues, and now finally we succeeded. There's 6 faculty members involved in this mission called Ultraviolet Explorer. Get launched in 2030. Okay. And everyone thinks Caltech people are very independent, they're prima donnas and so on. Well, I would say, yeah, fine, maybe. But 6 of these people are agreeing to work together. So I think, in my mind, in all these countries which are trying to catch up, the architecture of the department's wrong. We should have a simple rule. The department should give a mission statement that says, we wish to be number one in this. That's our goal. No, everyone can't have their wishes come true. but that should be the wish. Okay, so having these broad spectrum departments, comets or cosmology, hasn't worked.
Right.
Once you have something where a group of people are focused, there's actual energy that comes out of just the interaction.
Yeah.
And then if you have some success, then people from abroad or elsewhere want to come and be a part of the winning team.
Yeah.
No one wants to be a part of a vanilla team.
Yeah.
Everyone wants to be a winning team.
Yeah. Right. And just to add to that, right, we're in 2025 and, everyone in India somewhere, working towards 2047, which is going to be 100 year, since independence and all that. I think one area which you're also alluding to, as far as research is concerned, India is really not showing up on the map in terms of meaningful contribution. I'm sure there's some pockets here and there, but as the size of the country and the caliber of the people and the scientists like yourself who go outside West and do, incredible work, I think it's a huge challenge for the country. It starts with first acknowledgement. We have a problem and a determination and probably some bold moves to restructure things. It's how do we catalyze this whole ecosystem? But it is very important, a country of our size cannot take, research lightly and cannot be okay the fact that, we are not making meaningful contribution at the global level.
Well, I come to the conclusion that the two very big problems, and they're very different. One is what I call as the macro governance government. Okay,
Yeah.
they're mixed together. That is, at the highest level, the country as a whole, which means the government or prime minister and the cabinet, should take a view. Do we want to be seriously in the field? Do we seriously want research? It's not an obvious yes. Let me tell you why. You have countries like Malaysia, Indonesia, okay? I think their per capita GDP is higher than us.
Much higher.
Thailand, okay? Okay, maybe there are some universities I'm not going to put down, but they, as far as I know, that unlike what we used to have, the old Delhi University, Calcutta University, Dhaka University, Bombay, they're very famous.
Yeah.
Okay, then they've gone, now they've gone down, they're replaced by IITs, ISCT, and okay, some other things came up. As far as I know, I can't immediately tell you any of these things. Their whole economy works either on manufacturing, tourism, or goods, palm oil, whatever it is, okay? And they can be rich. And for most people in a country, that's good enough, okay? Korea and Japan, Japan has a few great universities in the top 500, but not more recently than before. For a long time, when they were in more of a manufacturing prowess, they had very deep connection between industry and academia, which is very research-focused for the exact problem. Industry would send their engineers to the US to do PhD, paying full fees and their stipend. Okay, so you can have another model where you get research on demand for what you're trying to do. The only time you really need, why do you need basic research? I think we should really ask this question. Because unlike other things in life, right, basic research is one of the few global activities. The example I give is, okay, all schools have a PE program. It's important. We have a body. We need to maintain that as much as our mind, okay? People like to watch, apparently, a lot of sports like cricket and so on. So it's important to set up the clubs so that there's a feeder. So when we have these games, people are, okay, so that's a part of the entertainment business. So we have physical PE program in school as a part of the regular body process. Then we have basically a PE program for entertainment like cricket and so on. Is there any then where does Olympics come in? And my view is, I would say it's very straightforward. The only reason you go to an Olympics is to show you excel. So even if India didn't go to the Olympics, you'll still do the cricket clubs, you'll still have the PE exercise and the thing, right? Because they're locally needed. So basic research is actually a global activity on part of humanity. And some countries may elect not to participate. So it has to be a choice you make. It's not a given to me, okay? And if you do make that choice, you should understand that this, you can't just say, culturally we want to do research. Yeah, fine, I get that. Because there are many things we do culturally. We like to have singing, we like to have
Right.
arts and so on. Okay. But even there, you can say like some of those things are not global. Okay, Bollywood songs may not translate so well to other places, and vice versa.
Yeah.
But science, no, it's this. So if we have to choose science as something we want to do in this country, then at the highest level there should be an acceptance that you have to have excellence, and that system of governance, funding, should follow the paths of excellence that have already been experimented and shown to work. Our model is simply nowhere close to that. Sometimes someone has said, why didn't you come back to Puffstone 2 But even otherwise, the bureaucracy level here is so stunning. I think it's impossible. I have such great sympathy now for my colleagues here. Ordering a part sometimes can take you a year. You get a funding letter for 3 years, and the money can come 1 year later, and the second year may come third year, and the third year may not come at all. So I think this is the top level. There's nothing I think neither you, I, or anyone can do until it's a national decision. And then there's a second level, which is, I would say, the way academia itself organizes.
Yeah.
And I would say the failings here are we no longer have pursuing excellence at every department level. I think we should replace that structure.
Yeah.
We should have funding that only goes, they say, yes, me and a bunch of people, we are actually trying to lead this in the world.
Yeah.
Please help us. And any generic stuff, I think we should stop doing it. It makes no difference to the world.
Yes, this whole mindset of playing to win. What we're saying is, first of all, the whole system probably needs significant reform and very meritocratic and driven, in some ways measurable, and a clear objective goal. Just focus on a few things and try to be among whatever top 3, top 10 in the world in that. But going to you're asking some introspective question also. See, like unlike smaller countries, we are nearly 17-18% of world population. If you go back to 20s, 30s, 40s, I think India had more research compared to US. US, it got heavily catalyzed in basically around the world, World War II and afterwards, and heavy funding by military and so on in 50s, 60s, and it has led to a lot of fundamental sciences breakthrough, but also enormous applied sciences, which has played a huge role in US being what it is. So I think there are many motivations why India should invest and what can benefit from. I think those answers are easy to arrive at, but how is that really requires significant political will and institutional reform, which is definitely beyond you and me.
Yeah, so I really thought, at least in the academic community, that there should be a frank discussions amongst the directors of these CET institutions and say, okay, let's look at the data and let's understand, what is. So I am making a very strong statement by saying, if basic research is to be pursued, its fundamental goals should be to aim to be the best in those areas, which many people I can imagine they'll object by saying, how do you know what is the best and so on? I know, and my view is no, I don't know what it is, and that what each group wants to do should be determined. My view is get the best people, let them figure out.
Yeah.
But you're not going to have a department of commerce to cosmology, 10 independent silos, and this department is not going to attract a bright person.
Yeah, I hope it gets this episode gets some people's attention and some food for thought. I think it's a broad, complex topic, and mindful of time as well, Shri. So perhaps we'll continue next time you invite me to Palomar facility, so we can then perhaps continue from there. But it's a very, very important topic. I want to just thank you for taking the time, sharing your journey. I'm pretty sure it'll be quite inspiring for aspiring younger researchers, as well as some serious food for thought of people who are deeply involved in the research ecosystem and care about India finally showing up at a global stage doing something. It will be probably multi-decade effort, but starts with a serious intention. So thanks so much for taking the time, and really enjoy the conversation. At SparX, we aim to bring to you stories of exponential impact. We share in-depth analysis of what goes behind success stories. If you find our conversations interesting, you can join us by subscribing to our YouTube channel. You can also listen to SparX on Spotify, Apple Podcast, or any other audio platform of your choice. If you have any suggestions on who we should invite or what topics we need to cover, just let us know in the comments. We are always listening, looking for ways to improve, and keep getting better as we go along.